Okay, I'm extremely happy to introduce today Dave Mount from University of Maryland. He comes pretty close to being a man who doesn't need an introduction, but let me spend a sentence or two. Among other things, he's been doing geometric computation of various kinds for many years, including lots and lots of problems related to nearest neighbors, approximate nearest neighbors, and things like this. And I believe that in some ways this talk is related to that. And I will let him speak. Please go ahead, Dave.
Okay, well, thank you, Boris. Yeah, what I want to talk about today is in part something that I'm very familiar with, which is, nearest neighbors and distances and things like that. And part of this is something that I must say is relatively uncomfortable or new to me, maybe some combination of those two things, which is the differentiable part of this. So let me get focus here. Oh, okay. So let me begin by mentioning the fact that, and I'm going to move the controls over here, that in computational geometry, right, there is this kind of tension always between the discrete and the continuous. For example, if I give you a set of points, I can compute the set of vertices that constitute the convex hull of those points, or, in general, maybe the combinatorial description of the polytope. On the other hand, I might also be interested in a purely, real valued, quantity like the area or, volume of the convex hull. Something like diameter, in the case of, for discrete information, I might want to find the two diametrical points, or I might want to know the distance between these points. And the focus of this talk is going to be on basically algorithms and data structures where the input is going to be from some geometric space, d-dimensional space as usual, and the outputs are going to be continuous quantities. So distances, areas, volumes, things of this variety, which change continuously as a function of the inputs. Now, I'm only going to talk about one such problem, which is sort of the distance to the nearest neighbor problem. But I guess I want to say that I kind of, I want to say generically, there's a lot of interesting questions that one could ask in this general regard. Okay, well, the first question is, well, why do you even need to talk about, continuous versus discrete things? If you can compute the discrete solution, if I know the vertices on the hull, presumably then I can, feed them into some formula that will tell me what the area of the convex hull is. Never mind the fact that there are some things which are very hard to compute, like, sums of Euclidean distances. But in practice, especially when dealing with multidimensional problems, you have to perform approximations. And the issue is that when approximations are made, they are almost never continuous as a function of the input. So for example, if I wanted to look at the diameter, a simple, very well-known heuristic or approximation is you just map the points to, a nearby set of grid points. You then compute the distances between the grid points, and then you return the farthest pair of grid points, okay? This will get you, depending on the size of the grid, a 1 plus epsilon approximation. Of course, as the points move, the points on the grid to which they're going to be snapped is going to change discontinuously, not to mention the fact that the grid itself might, change discontinuously as the sort of the diameter changes. And as a result, you can make an infinitesimal change to the input, but have a, a constant, change to the output. So therefore, these things are not going to be continuous in general. So why do you care about continuity? Well, assuming you're not looking at purely combinatorial questions, there are lots of problems where continuity is important. Navigation and docking, for example, if I'm trying to, parallel park my robot into its parking spot or something like that, I need to know things like the distances to the close by obstacles. Where's the curb? Where's the car in front and behind me? Where are there any pedestrians that I'm going to be running over? And of course, the issue is, as I am slowly moving into my spot, I do not want it to be the case that a very, very tiny movement by the vehicle results in a discontinuous, modification of where my nearest distance is, because of course that could result in me having to, suddenly change my plans, let's say. But there are lots of other applications of these things, shape modeling, density analysis in computer graphics. This new technique called Gaussian splatting is very popular. These techniques all talk about the fact that they are not just continuous, but in fact they're differentiable. Oh, and the last one I should mention, which is this massive area, which is I cannot seem to go to a talk these days which does not talk about differentiation, mostly because it's people who are doing work in deep learning. And the way you basically do training in deep learning is by this process of backpropagation, which requires you to do gradient descent, which assumes that you have a function that is, continuous. And so the idea of producing differentiable, measures is becoming a very important topic in computer science in general. Now let me kind of give the disclaimer, which is, and I think this may apply to a lot of the members of the audience, which is the reason I got interested in computational geometry in the first place was because I did not want to do multidimensional calculus, right? I didn't want to be computing Gaussians or Hessians or Jacobians or Hamiltonians, or I didn't want to be computing eigenvalues or eigenvectors. What I liked about computational geometry was it's just, compass and straight line. It's like Euclidean geometry. It's easy to understand, easy to appreciate. So it's kind of, I feel a little bit guilty, like I've been, sort of dragged into the, I don't know what you say, the, maybe, enticed by the dark side of the force or something like this. Actually, I'm going to blame it all on Ahmed. Ahmed is working, he's a former PhD student of mine, he's working at Google. And, everything these days is, it's deep learning based, differentiable, continuous, and so forth is very important for these guys. So the issue that I mentioned before is that approximation is the enemy of the continuous. Approximation relies on rounding, snapping, bucketing, histogramming, anything which is sort of conditional, like it depends upon, distances and things like that. All of these things are, problematic when things move because the decisions that you're making are going to change. So let me give an example of what goes wrong, from the perspective of, my favorite topic, which is nearest neighbor searching. So, if you think about, the notion of a Voronoi diagram, well, let me think in terms now of not identifying the nearest neighbor, that is a discrete problem. But the distance to the nearest neighbor, I can think of this as kind of I can't really draw this very well, but my little circles here are to suggest the idea that this is a topo map, topographical map. By the way, for those of the people in the audience who are old enough to remember what a map is, right? You used to get these USGS maps when you'd go hiking, and these things would have these little contour lines that would indicate, how high you are. And your distance from your nearest neighbor, of course, can be thought of as this function. Okay. The idea is it's zero, right where the point is, and it grows in this, cone as you move away from the point. And then, of course, the ridge lines between two of these cones meet right along the Voronoi edges. Well, the problem is approximation is going to decompose things into space. For example, using like a quad tree would be a very natural way in which to do this. Each cell of the quad tree, right, you decompose the cells until sort of you are within the epsilon error that the user has provided to you. And then each cell is just going to decide who the nearest neighbor is. And so the idea is, I hope you can see can you see my cursor? The idea is that for each one of these cells, you just sort of specify, who is the nearest neighbor. And so the idea is as you jump from one cell to the other, even though you're not on the Voronoi edge itself, where distances would vary continuously, you're going to be off the Voronoi bisector, which means the distance is going to change to the representative, let's say, it's going to change discontinuously. This is a problem. Why? Well, because as I mentioned before with this little parking example, these discontinuities can cause oscillations. So here's a little example. I have 2 points, blue and red, right? I decompose space into regions according to who is closer. So for these cells, the blue point is closer. For these cells, the red point is closer. And given a query point, let's say I want to do a gradient descent and I want to move to my nearest neighbor. Well, from the blue cell, I'm going to first, right, move to the blue point, but my gradient step, in the worst case, might lead me into a red cell. From there, I'm going to do the gradient descent as well, right? And you can see what's going to happen. That's going to lead me potentially into a blue cell, which can lead me into a red cell, to a blue cell, and a red cell. And these weird oscillations, although I've designed this one very carefully, these weird oscillations actually do tend to occur with a lot of control systems that are based upon approximations and have discontinuities. You will see situations where a solution is moving continuously and then it starts, jittering before it kind of stabilizes. And the jittering is causing when you're very close to a decision boundary and it's sort of discontinuous. By the way, I'll mention, please feel free to, ask questions if you like. However, I'll say that I hid all the controls. So if you ask anything in the chat, I won't be able to see it. So maybe Boris can interrupt me if there's any questions that come up that I need to address. Okay, so here's the question that we want to consider kind of generically, which is I would like to, assuming I'm given a differentiable continuous function, right, in real m-dimensional space to real space and some error-bound epsilon, I want to produce a differentiable function f tilde that is a epsilon approximation to my original function, let's say, in kind of the standard sense. I'd like the function that I produce to also be differentiable, okay? I would like my algorithm not only to output the function, but I would like to output the gradient as well, because again, I would like to be able to perform gradient descent using these functions, maybe put them inside of my neural nets or whatever it is I'm doing. And then I would like, ideally, the function to not be any more wobbly or, I guess, what do I want to say? Vary more than it needs to. So I would like the gradients and Hessians to be close to optimal in some notion of what I mean by optimal, I guess. And I would like the computation space and time to, as much as possible, match the best algorithms for a non-smooth approximation. That would be certainly ideal. Let's say that I don't have to pay any price for that. I would also like to preserve kind of global properties of the scalar field that I'm working with. For example, if there are unique local minima, I would like my algorithm or my approximation to satisfy this. I'll tell you, by the way, I'm going to be able to succeed on the first 3 points. This last point, I am just going to leave as an open problem, because the final solution I'm going to produce, if you think of it kind of like, smoothing a terrain, when we do this smoothing process, there are going to be places in the terrain where we're going to get little dips and valleys and things like that. And it is going to be possible for our algorithm to kind of find local minima where, they are not the proper minimum, let's say. Okay, so as I said before, I want to work with the problem of nearest neighbor searching. And let me just check to see if I can see what my time is. Okay, let's just see what nearest neighbor problem looks like in this setting. So let's think, what is the function here? The function is that for any given point x, right, I want to find the distance to the closest point. So in standard nearest neighbor classification, you want to know the identity of the closest point. All I want is the distance to the closest point. Okay, I can think of this as modeling a function where, the function that I'm modeling is the distance function. Actually, let me step back here. So this would be the exact distance. I'm going to allow an epsilon error, which means that I'm willing to accept any distance that within a 1 plus epsilon factor of the true nearest neighbor. The problem is, in dimensions higher than, 3 and higher, let's say, I'm going to face a high combinatorial complexity if I wanted to store this information, the entire function itself. I'll mention, by the way, that I'm going to actually use squared distance instead of Euclidean distance, mostly because, for computing things like derivatives, it's just easier to work with the squared distance. It's for example, one of the issues with the Euclidean distance is the derivative is actually not defined at the points themselves. Which is kind of weird. The nice thing about squaring is you get something which is differentiable everywhere except right where, the functions are meet, right at the ridge line. You essentially have something that's non-differentiable. And the observation I want to make is that squaring doesn't have a huge impact on the approximation. It turns out by using just a slightly smaller, maybe epsilon over 2 or epsilon over 3 approximation error, you can essentially work with the squared distance. Okay, so, and these are kind of standard facts. I'm not going to maybe justify these things. But so here's the problem. The problem is if I'm given a point set P, discrete set of points, I would like to compute these approximate distance functions and the gradient for those functions with the following approximation guarantees, right? The distance that I produce should always be greater than or equal to the true distance and should be less than or equal to maybe 1 plus epsilon times the true distance. Throughout, I'm going to assume that the dimension d is a constant, and I'll just say that, yeah, this is usually where the machine learning members or the people who got into who started listening to the talk because they were interested in machine learning kind of turn it off. But this seems to be a restriction of, sort of the techniques that I'm working with here. But, trying to figure out how to do this, let's say, with something, with complexities that are polynomial in D, I'm going to have factors that are going to be exponential in D, which is going to be a problem here. Getting factors that are polynomial in D seems to be a significant, problem in this area, let's say. At least I don't know how to do it. Methods like locality-sensitive hashing would be natural candidates to apply these methods to, but I don't know how to do that without blowing up the complexity. Okay, so here's the main result. The main result is we're given a point set of size n in d-dimensional space. I want to compute a differentiable approximate nearest neighbor data structure. Okay. I would like the space to be pretty close to what the best space is for the AVD data structures that's out there. The query time to be essentially the best, matching the best. I would like to return the gradient. And finally, what else? I would like to compute the Hessian and the gradient and the Hessians. I'd like those to be close to optimal. The claim is that gradient, this is for the regular Euclidean distance function, that has a slope of just 1. The gradient's going to be something like square root of d. And our gradients are going to be about the same size up to constant factors. The Hessian is going to grow something like epsilon over the distance, but the claim is that this is about as good as you can do, and the argument as to why that is the case is just to observe that what happens when you get right to the ridge on the Voronoi bisector between two distance functions, the function essentially has to smoothly transition from one of these functions, let's get has a slope of +1, to another function that has a slope of -1, and it's only got about an epsilon times the distance in which to do that transition. And so you can essentially argue that you can't really do any better for the Hessian, at least when you get to these border points here. Okay, so this is the result that I want to talk about for the rest of the talk. Let me begin by saying that there are lots of, at least, well, first off, if I try to even cover, differentiability in the broader scheme of mathematics and computer science, I would not have, this would just be impossible. But at least within sort of the theory and computational geometry world, there have been a number of people who've studied the issue of differentiability or Lipschitz continuity or stability, however you want to describe it, in various forms. There have been a number of works that have to do with Lipschitz continuity for graph problems, covering problems problems you would think of as just being purely discrete, minimum spanning trees and things like that in graphs. Mulemans have looked at, and kind of other computational geometers have looked at the notion of stability. The idea is if I make tiny changes to my input, I would like, my structure to change only a small amount as well. Uli Bauer looked at topological stability, like is in the question of if I'm computing, I don't know, trying to minimize the number of critical points in, representations of objects. Looking at similarity of Markov chains, in differentiable, measures of distance between these things and so forth. And then the other topic that kind of comes up in this area is the notion of regularization. Regularization refers to the notion of smoothing. So, if Joe, I guess, is still on the call here, you may recall that we had done some work on the discrete geodesic problem. One of the questions are, how do you smooth the geodesic function, let's say, to produce a reasonable approximation? And this would be sort of a nice question to look at. It has been looked at from the view, I guess, the world of, solid modeling and computer graphics. Okay, so let me kind of get to, the techniques here. So the first idea is, well, why don't you just, you kind of gave this example of where you tried to build your, approximate Voronoi diagram. You break things into cells, you build a representative. Why don't you just do that, but maybe be a little bit smarter about how you choose your representative? The point that I want to make here, I would call such a thing a witness-based approach. That is an approach in which what the algorithm is going to return is a distance to a single point. The claim is that any approach that is based upon computing the actual distance to a single point is going to be doomed. And this was a lemma that Ahmed and I proved, that basically if you're dealing with a point set of finite size, basically a discrete set of points, that no witness-based approach can be both continuous and guarantee relative errors unless it is an exact algorithm. So in other words, it really can't be an approximation algorithm. And here's the reason why. Suppose you have built an approximation algorithm for computing nearest distances. And suppose at any point x, it fails to actually get the true nearest neighbor. Like, let's say it returns the distance to this point instead of the true point, this one over here. Well, you can break this algorithm as follows. You just continuously move the point closer and closer to its true nearest neighbor. And as you do so, your relative error is going to get bigger and bigger and bigger. When you get to the true nearest neighbor, the relative error is going to go to infinity. So no matter what error you're guaranteeing, there will be some point along this trajectory where you are going to break your bound, your error bound, and you are going to be forced at that point over a very tiny distance, whatever that distance will be, to make a discontinuous jump to the actual true nearest neighbor. So when that happens, you cannot have continuity. So this would seem to sort of doom you, but here's going to be the idea. Rather than computing the distance to a single neighbor, what I'm going to do instead is I'm going to return basically a blended distance to a constant number of near neighbors, okay? So what I'm going to return is going to be, like I said, you can imagine I've got a neighbor over here, and another neighbor behind me. And what I'm going to do is I'm going to average, in some regard, the distance between those points. And as I move, the point that I'm moving away from, its weight is going to decrease, and it's going to have a smaller effect, whereas the points that I'm moving towards are going to have a larger effect. So here's the idea. We're going to start again with this kind of quad tree-like subdivision. I want you to think of approximating the Voronoi diagram. Let me emphasize that our algorithm never computes a Voronoi diagram, but it's easiest to understand it in these terms. So you're going to start building a Voronoi diagram where you split and split and split, getting basically in the areas where you need to split. You need to split in areas that are close to the Voronoi bisectors, right? In this region here, you know who the nearest neighbor is, but along these cells that are sort of right near the bisector, yes, you have to keep refining until you have sort of this epsilon error. Now the idea then is each cell will store a nearest neighbor representative. And so, for example, all these blue cells have stored this point as their nearest representative here. And I do this for all the cells. Now, as I mentioned before, this is not going to be continuous. So this is where the next idea comes in. Let's zoom in on a portion of this picture here. Okay, and let's take a look at these cells, maybe right around this Voronoi vertex. So each cell is going to define a little patch. Okay, think of that patch as being a sphere that's going to enclose the, the quad tree box, okay, for this thing. And my quad tree box is going to store essentially a representative, that is the distance, to this nearest neighbor, okay? And so I'm going to have a distance function that's based upon that one nearest neighbor. A neighboring quad tree box, right, is going to have a different one. So this red cell is going to have, store the neighbor to this point in the red Voronoi cell, and the blue guy is going to store the distance to the blue point over here. And then what I'm going to do is I'm going to blend between these, let's say for all of the quad tree boxes whose enclosing patch, which is usually the term that's used for these things, I'm going to average amongst all of these things in a smooth manner. So as the query point moves in this region of overlap, the relative weights that is given by the distance to the green point, the distance to the red point, and the distance to the blue point are going to slowly vary. That's a very nice and simple idea, okay? This, by the way, is called the partition-of-unity method, and it's been around for many, many years, sort of from the area of finite element analysis. And you can kind of see why this has something to do with, finite elements, right? If you were decomposing space into regions and you want to smoothly interpolate, that's exactly the way it seems like a very natural way in which to do this. At the end of the day, right, instead of having a quad tree decomposition, I'm going to have a bunch of overlapping patches, and then I'm just going to smoothly blend. So as my query point wanders from cell to cell, the patches that it's overlapping are going to, change gradually. Now, I have to make sure that when I cross these boundaries between cells, basically there's not going to be any dramatic transition there. And the way this is achieved is through this method called partition-of-unity. And I'm going to just zip over this because it's, why this works is all, it's all calculus. And like I said at the beginning of the talk, this is the stuff that I really don't like, but the idea intuitively is relatively easy to understand. So I have a patch, call that pi sub 1, let's say, that I want to average over. I have a function that I want to average over that patch. I have a weight function. The weight function is going to be 0 everywhere outside the patch. And when I come into the patch, the weight is going to increase to some large value. And as I get to the boundary of the patch, it's going to go back to 0 again. Okay. Let's say I have another patch, pi 2. It's got its own weight function, let's say. And then what I'm going to do is I'm going to blend between these patches, right? So the way I do that is I'm going to have a blending function phi, which I take my psi, I divide it, I normalize it by the total weight of all the blending functions. Now, the only blending functions that are going to contribute to the sum are going to be those patches that overlap my region. So even though I'm going to have a very, very large number of patches over the entire, space, at any given point, there's only going to be a constant number of patches that overlap. So only a constant number of these guys need to be blended together. And the final approximation is going to come by just averaging these blending functions times the various weights, right? And so the idea that you can sort of see illustrated here is when you're over patch pi 1, that function has all the weight, so you're adhering to that. When you're over patch pi 2, the function f2 has all the weight. And when you're in this region between pi 1 and pi 2, you slowly and gradually, lose the influence due to f1, and you gradually, increase the influence due to f2. So you just smoothly interpolate between those two values. Hope that makes sense. Okay. What are these weight functions and how do you do these things in, higher dimensions? Well, again, I'll just kind of zip through this stuff, but it's fairly, I guess this is fairly standard. First off, you have this smooth bump function that has this property that, outside of, it has constant support over basically -1 to +1. It's 0 everywhere, and here it increases from 0 up to a maximum value of, I guess, 1 and then back to 0, or let's say a maximum value, whatever that maximum is. yes, the shape is going to be given by a shape function. So I've been talking about using a little ball. Well, the shape function here is just going to be the equation for a ball. And then the way I get my weight function is I take my shape function, which goes from 0 at the center, right, of my ball out to a value of 1 when I get to the edge of the ball. And I just plug that into my bump function. And so that produces my little spherically shaped bump, right? It is smoothly 0 right at the boundaries of the ball, right? And then it goes up to some maximum value. So going back to my previous picture here, right? Because of this smoothness, whenever I cross the transition between one of these, balls, I'm actually just there. I'm absolutely at 0. And then as soon as I enter the ball, I'm going to start ramping up smoothly up to the next higher value. Okay, so this is the idea of the partition of unity. Very simple. The next question is, how do I employ that in the context of nearest neighbor searching in an efficient manner? Well, there are a couple of issues here, and these are the data structures issues that I have to sort of deal with. The first of these issues has to do with the fact that I don't want to have too many, for any given query point, I want to blend a constant number of different functions, maybe at worst a logarithmic number. In fact, our method only has to blend a constant number, but the idea is, you don't want to have to blend over all the points in your data set. That's not going to be efficient. And the problem is that as I've described the patchwork system here, right, if you have, let's say, quad tree boxes and each of them is growing a neighborhood ball, the issue is that these balls could have an arbitrary degree of overlap at any given point. Okay, so this is a problem. The fix for this is, well, the reason this comes up is because quad trees kind of shrink too quickly. But there's a simple fix, and this is a fix that's kind of well known to people who work with quad trees. It's called either restriction or smoothing or whatever you want to call it. What you do is you kind of refine the quad tree so that they don't change so quickly. Okay, you want to have sort of a smoothly varying change, which of course has to do with the size of these little disks here. But if you do it properly, what you can guarantee is any given region of space is only going to be overlapped by a constant number of points. Now you might say, well, I have to add a whole bunch of additional boxes to my system. But one of the cool facts is that you can do this while only increasing the number of quad tree or number of cells in your quad tree decomposition by a constant factor. It depends on kind of, how smooth you want the variation to be. But this is nice, let's say, that there's no significant difference in the number of boxes that you get. Okay, that's the first improvement. The second improvement has to do with, well, this is a Dave Mount thing, I guess. The Dave Mount thing is, when I look at this decomposition, I think to myself, wow, look, you got an awful lot of, quad tree boxes that you're using to cover this little edge here, right? You have this long edge and lots of little boxes along there. It seems somehow inefficient to do that. Here, let me blow that picture up. Yes. So here's the idea. I would like to cover these things more efficiently. And for those of you who know me, you know the word McBeath is about to appear in the next few slides. Okay, here's the idea. We're going to expand each one of these Voronoi cells. By the way we do the expansion is a little bit tricky. Here I'm just kind of moving the sides by some fixed distance, but we really have to be a little bit more clever than that. But the moving of the sides by a fixed distance is to make sure that I have things that are kind of still look like nice convex polytopes. Okay, what I'm going to do is I'm going to cover each of these cells. I want to cover the inner guy with a set of ellipsoids, okay, with the property that the ellipsoids are all within the expanded region. I want to think of the expanded region as, as long as you're in the expanded region, you're still guaranteeing an epsilon error, in your nearest neighbor. Okay, so the claim I want to make is this is a lot better than using these little, sort of isotropic elements. By using these ellipsoids, I can use many fewer ellipsoids to get, coverage versus the number of quadtree boxes that I would have to use. The way this shows up in the complexity bounds is basically the 1 over epsilon raised to the power d. Those factors become 1 over epsilon raised to the power of d over 2. That sort of is the improvement you get from using an ellipsoid-based approach. Where do these ellipsoids come from? They come from this idea that I really love called McBeath regions. Okay, McBeath was basically this idea was developed in the mid-1950s for completely different reasons. Imre Barani basically made a career out of using McBeath regions for solving tons of problems in convex geometry, all things having to do with approximation and things like that, the economical cap cover theorem and so forth. And with Sunil and Guilherme and other co-authors, we've been using these McBeath regions for a lot of geometric approximations. So here's how this works. I give you a convex body. In our case, let's say a convex polytope. Think of that as a Voronoi cell. To build a McBeath region, what you do is, you pick a point at which you want to have the McBeath region place, call that X. You essentially reflect X, right, around the point X, negative, basically K, I'm sorry. K being the body, you basically reflect it about, so X minus K. You intersect those two shapes, and then you shrink it by a constant factor. Typical shrinking factor is something like 1/2 or 1/4 or 1/5 or something like that. It doesn't depend on the dimension. There's just kind of a shrinking factor that you use there. And then what you do is you throw a John ellipsoid inside of that thing. Okay, that has the nice feature that, as you move this thing around the boundary, it does a nice job, the McBeath region does a nice job of adhering to kind of the geometric shape around there. Ultimately, of course, we have to build kind of a hierarchy of these things. So you have very big ellipsoids at the highest level, which go to smaller and smaller and smaller, and you build sort of a layered DAG, which allows you to search for these things. In the context of the Voronoi regions, what we do is we actually are going to build this expanded Voronoi cell. By the way, where does this expanded cell come from? It comes from the following place. What you do is you actually do the lifting. You lift this thing onto the paraboloid. You look at one of the, this is something that a computational geometer would understand, right? So if you think of the Voronoi diagram as this polytope of points on a paraboloid, you take each of the facets of the polytope and you push it up, basically by a distance proportional to epsilon, okay? And what that does is that gives you an expanded region here. And so what I've drawn here is, this is just, from the viewpoint of the polytope, if you project that thing back down, this is essentially one of these lifted regions. And then you just apply this construction up in the lifted space. So you're just going to build a D plus 1 dimensional ellipsoid, and then you're going to project that thing back down. Okay, so this is the main idea that I want to describe for, I guess, beyond the quadtree. So let me kind of very quickly go through the nuts and bolts of the construction here. These are the following. So first off, I do have to start with a quadtree decomposition just to get things started off, but it's a fairly what I call a weak quadtree. It's not this, refined all the way down to the epsilon level. In fact, this is entirely independent of epsilon. We just want to build a quadtree that allows us to establish some very, very weak separation properties. Every quadtree cell should be at least a constant distance from the nearest points, but it's allowed to contain a single point of its own. Or the other thing that can happen is I can have a cluster of points. Oh, is there? Oh, okay. I can have a cluster of points that are going to be somehow separated from a quadtree box here. Okay. Okay. So this is the idea that I have here. This is the weak quadtree construction. I won't talk about it because we discussed this in previous papers, but the idea is you can build this thing in n log n time. It has O of n size independent of epsilon, and depth basically log n. You can find a point that which cell contains a point in log n time. And it's just a kind of a smart quadtree decomposition. You by and large, you're just building a regular quadtree, but to handle these deep clusters, you have to do this business of kind of shrinking. This is kind of a, path compression, the kind of thing you do in a Patricia trie. You zoom in on very, very dense regions, and then you have to do a little bit of balancing on the resulting tree. The final construction works like this. You build this weak quadtree for every one of the cells in your quadtree. And the most interesting case is when I have a big cell and a small little cluster of points. What you do is we subdivide the quadtree into rings based upon distance. So we look at twice the distance, 3 times the distance, and so forth from this kind of central cluster here. And then within each one of these little cells, we're at roughly the same distance from our nearest neighbor. We're going to build an ellipsoid decomposition for those guys. We go out to the next level. When we go to the next level, we can make a little bit bigger error. So the difference between, this and that is we can use a slightly larger, absolute error because we're twice as far away. So our ellipsoids are going to be a little bit bigger, and we just keep continuing building these ellipsoids out until we have essentially covered the entire cell. Here I've just done it for one of the Voronoi cells, but I would do this actually for all the Voronoi cells that intersect W. We're going to add a hierarchical structure so we can do searching on these things. And then finally, I go back and I use that, Babushka and Melenk, that partition of unity to smooth between these ellipsoids. So that's the whole idea, pretty much in a nutshell. I won't go through the messy details, but basically the size, the n factor comes from the quadtree, and the 1 over epsilon to the d over 2 is coming. Actually, this probably should be d over 2, not d minus 1 over 2. I think that's a typo. That is coming from the fact that you're doing these ellipsoids and the fact that you're using the McBeath regions. As I said before, the McBeath regions, if I'd just done the quadtree, I would have had an epsilon to the d. Using the McBeath regions, you get the d over 2, so you sort of have the exponent there. And the depth is really going to be log n for the quadtree, and there's going to be an extra log epsilon for the going through the ellipsoids. Okay. How are we doing? I kind of want to wrap up. There's a number of, again, more not combinatorial, but mathematical kind of numerical issues. The first thing is that when I began the talk, I said, well, you're doing, smoothing over these nice little spherical patches. Okay, but now we've got ellipsoids. So I have to be able to smooth over sort of a spherical patch intersected with an ellipsoidal patch, but that's not a big deal. Okay, what happens is you will have a smoothing function for, a spherical patch. You'll have a smoothing function for a ellipsoidal patch, and to smooth between the intersection of these guys, you just have to take the product of those two things, right? Because if you remember, both of those things go to 0 when you get outside of that area. So by multiplying these guys together, when either of them goes to 0, the whole thing goes to 0. So again, sort of technical issues that are involved there. The other thing that I mentioned before is I want to show that the gradients and the Hessians are pretty much, within constant factors. So the gradient, the claim is the gradient is going to be just a constant. And the reason is this, that the number of patches that's going to overlap any given point is only going to be a constant. I didn't prove that, but let's say take my word for it. So you're blending a constant number of functions. Each of those functions has a gradient whose norm is a constant. So it's going to follow that the sum of the gradients is going to be a constant, depending on that overlap. And then the other comment I made about the Hessians is the claim is, well, the Hessians are going to have to be fairly large, because if you look again at those ridge points where you are changing between one, the distance to a point on this side and a distance to a point on that side, you've got to make a transition. We show that the value of the Hessian, the norm of the Hessian is at most this 1 over epsilon to the distance to its nearest neighbor. I will say that that is not easy to justify. Okay, if you want, you can read it in the paper, but I said at the beginning of the talk that, I never wanted to compute a gradient or a Hessian in my life. I'm really unthankful that Ahmed was patient enough to go through these things. So he went through this, he continued to go through this, he continued to work through this, continued to work through this. It took a lot of work to actually figure out exactly what the bounds were on the Hessians and the gradients. And like I said, I am so thankful that he did this, because I would myself never have the patience to go through it. But at the end of the day, you actually can get these bounds on the gradients and the Hessians. Okay, so to summarize, what I have shown here is that you can compute distances to nearest neighbors. That is the nearest neighbor field in a manner that is differentiable. Okay, how is it done? Well, it's done by very much the same mechanisms that we would have used for like an AVD approach. But you build the AVD, you partition space into lots of little regions such that normally the answer would just be, well, each region computes a representative and you use that representative to compute the nearest neighbor. Here what happens is we kind of let the regions bleed out into neighboring regions in such a manner that each region, let's say any point in space, is only overlapped by a constant number of these guys. And we use the partition-of-unity technique to smooth between these various sorts of things. Now, at the end of the day, we prove that what you have is smooth. And because it's based upon the same techniques that were developed for the AVD, it has essentially the same complexity in terms of space and running time and so forth. And as I said, thanks to Ahmed's diligence, we can prove that the gradients and Hessians are pretty close to what the best possible. There are still many things that we would like to do. First off, as I mentioned earlier, in order to apply this stuff to anything that would be sort of interest to the learning community, you have to make this work in really high dimensional space. And the problem is, it's the bleeding that does this to you, right? The problem is if you have a multidimensional subdivision, okay? In fact, this is why even LSH, it's a problem. Anytime you build a grid, as soon as you let things bleed from neighboring grids into surrounding grids, you're going to get this, at least a 2 to the D kind of effect. And I don't know how to basically get around that. That seems to be kind of a fundamental issue with the whole partition-of-unity method. The second thing that I mentioned before is, we put bounds on the gradients and Hessians, but to be honest with you, I don't really know what is going on, like when I start blending all these guys together, what kind of little dips and valleys and things like that are we creating here? It is smooth. The gradients are bounded, the Hessians are bounded, but like the critical points, how many, little, like I say, little ugly things are going on here? How many saddles, local minima, and things like that am I creating? I have no idea. This seems to be a very important question, though, if I'm going to do things like gradient descent. And then the last thing I guess I want to mention is that we did this for a very simple example of distance, just distance to a point set. How about other distances? Could I compute things like, what I wanted to compute, maybe my distance to my kth nearest neighbor, or what if I wanted to compute geodesic distances? Or what if I had distances between point sets, things like the chamfer distance or the earth mover distance or things like that? In fact, in general, I would just say take any problem from the, from the literature in computational geometry where there is a notion of a real valued output that makes sense. The question is, can you make that thing differentiable or not? Okay, that seems to be an interesting question. And so I would just like to sort of, leave you all with that general thought. So with that, let me just say thank you and